Yeah, is that working? Okay, no, it should be on now. Okay, sorry about that. Okay, fine. Okay, so this is the fourth set of slides, and just think about it in terms of sets instead of lectures because we're not exactly lined up anymore. Okay, so this is the outline. We'll start with a summary of the last lecture, and then we'll get into information theory, which is the theme of today. So essentially, we'll cover, hopefully, all of what I want to say about this topic, which corresponds with chapter 4 in your textbook. Okay, so in some sense, today's lecture, this material, is going to serve as a bridge between what we've seen so far. So we spent about 3 lectures talking about propagation, and hopefully you're mastering that topic by now. And we're going to spend the next 3 or 4 lectures, maybe even more, talking about digital communication. So we talk about modulation, coding, and diversity. And today we're going to talk about information theory. And as I said, this material is going to serve kind of as a bridge between these 2 different areas, which are connected through information theory. Okay, so we'll talk mostly about capacity of different channels with different degrees of information. So we'll see what that entails in a second. First, let's start with a summary of what we saw last week. So after that, we had spent about 2 weeks or 1 week and a half dealing with large-scale propagation, path loss, and shadow fading. Then we spent another lecture and a half talking about small-scale propagation. So about what happens over very short distances that are on the order of the wavelength. And for this study, we assumed that the large-scale phenomena were locally stationary, so the path loss and the shadow fading were fixed. And so we're looking at short distances or short time intervals over which shadow fading doesn't change significantly, and all that changes is the multipath fading. And we saw that we can characterize this multipath fading through a linear time-varying impulse response that may or may not have line of sight components, depending on whether the line of sight is blocked or not. We saw that because of motion, each of the multipath components experiences a different Doppler shift that has to do with the speed of the mobile and with the angle of arrival of that particular multipath component. So that's what we call the Doppler spread. Actually, the Doppler spread was the interval containing all these Doppler shifts. So if we send a tone at frequency fc, we receive multiple tones, 1 per component, and their frequencies all fall within the interval fc minus fd and fc plus fd. So we can have a shift of up to plus or minus fd. What fd is the Doppler spread, and it's given by the speed, v, times the frequency of the signal, f sub c, divided by the speed of light. Okay? Very important formula. And then we saw also that the reciprocal of this Doppler spread gives us a rough idea of the coherence time. So this is the time over which the channel remains more or less constant before it changes into different boundaries. Sorry about that. Then we saw that the different multipath components not only come up with different angles and so have different Doppler shifts, but also have different lengths in general, and so different delays. And therefore, the signal is also spread in time. So we have multiple arrivals that come in with slightly different delays because of these different path lengths. So we characterize this spread in time through the concept of the RMS delay spread. And we saw a formula of how to compute it from the power spectral power delay profile. We saw that the delay spread, or its reciprocal, which is the coherence bandwidth, allows us to classify channels into 2 distinct classes. We had, first of all, narrowband channels, for which the frequency, the fading is frequency flat. And then we had wideband channels, for which the frequency, the fading is frequency selective. Okay? So the channels were narrowband when the delay spread was short relative to the symbol time, or equivalently, when the coherence bandwidth was small relative to the signal, to the bandwidth of the signal. Okay, and we had on the other hand, we had that the fading was frequency selective, or the channel was wideband if the coherence bandwidth is much larger or comparable at least to the bandwidth of the signal, or equivalently, when the delay spread is significant with respect to the symbol time. Significant meaning comparable or even larger. Okay? So in the narrowband case, the fading amount suggests a scaling, a time-varying scaling, which we model as a random process. And in the wideband case, the characterization is more difficult, and we have intersymbol interference distortion. So we have this fact that different symbols arrive with different delays over different paths, and so adjacent symbols are going to interfere with each other. That's what we call intersymbol interference or ISI distortion. We saw that by means of the central limit theorem, if the number of multipath components is large enough, then the fading process becomes an approximately Gaussian random process. And as such, it can be fully characterized by its mean and autocorrelation, and its amplitude is going to be randomly distributed. In the case that there is no line of sight. If there is line of sight, then it becomes rise. Okay? So we studied this mean and autocorrelation in quite a lot of detail, and we drew particular insight in the case of this simplified Clark-Jakes uniform scattering model. So for that one, we were able to derive a very nice formula using the Bessel function for the autocorrelation. Okay? And finally, we saw that another effect of the multipath channel is that it randomizes the signal polarization. So we'll revisit this in a couple of lectures when we talk about diversity. Okay, so before we start with information theory, any questions remaining in your minds about all this stuff? I hope the homework was helpful at forcing you to go to the notions and the concepts. But if you want to make a last question, nothing? Okay, good. Okay, so let's start with information theory. And I believe there is a course, I know there is a course here, I think it's on this semester, in information theory here at Columbia. And it's also on CVN. So those of you who are in graduate school or who are thinking of going into graduate school in anything that has to do with communications, I would encourage you to take a course in information theory at some point, because it's a topic that lies at the core of communications and data compression. So I really encourage you to learn about it. Information theory, in contrast with other disciplines whose origins may be kind of mystic, information theory has a very defining birth date and a very defined father. So information theory was born in 1948 with the publication of a paper entitled A Mathematical Theory of Communication, and authored by Claude Shannon, who was at the time a Bell Labs researcher. He then went on to become a professor at MIT. So he's probably the most distinguished researcher in the history of Bell Labs. So at the entrance of our main building, we have two statues. We have a statue of Graham Bell, after whom the laboratories are named. And we have a statue which is of Claude Shannon, which unfortunately is not very visible here. But anyway, I think the point is made. So Shannon's work is nothing short of revolutionary, and it is arguably one of the greatest scientific contributions of the 20th century. There is little dispute of the fact that the publication of his paper in 1948 marks the birth of the information age. So before Shannon, it was believed for many years that the only way to reduce the error probability when communicating data was by either increasing the power or reducing the data rate. So for example, in the 19th century, when the only way of communicating data was by telegraph, Morse code over telegraph lines, they thought the only way to reduce the chances of mistakes in the message was to just send it multiple times. The more times you send it, the fewer errors. And if you want to make sure that it's received without errors, you have to send it an infinite amount of time. an infinite number of times. So it was believed that the only way to make the probability of error equal to 0 was by making the data rate also equal to 0, or by increasing the power. So that was the belief at the time. And Shannon proved that was completely wrong. So Shannon proved that at any given rate and any given power, the error probability can be made as small as we want by using coding. okay? As long as the rate at which we want to communicate is below some channel capacity for the power level. And this notion of capacity, which we'll define in a little bit, is something that that did not exist at the time. So it's something that Shannon came up with. So what is coding, which I mentioned here in this statement? Well, coding entails introducing control redundancies and dependencies in the data. Okay, and we'll spend 1 or 2 lectures, maybe just probably 1, on coding. So we'll see some basic codes, maybe some of the ones that your cell phones use, and how they work. But the idea in coding is to introduce dependencies and especially redundancies in the data. Okay. So Shannon proved that. He proved that without increasing the power, without reducing the rate, you can reduce the error probability as long as you don't violate this rule, as long as you don't exceed what capacity. He also proved the converse. So he proved that if you exceed this capacity, so if you try to communicate faster than this capacity is going to tell you, then there is no way that you can make the error probability be small. It's always going to be large. So he proved that. And that was in 1948. So for 57, I guess 58 years now, the art of coding has evolved in search of ever better codes that could achieve the performance promised by Shannon's results. And after these 58 years, today we have codes that operate very, very close to capacity. Okay? Very, very close. But it's taken several decades. Always keep in mind that the notion of capacity is not bound by complexity or latency considerations. So approaching capacity requires a lot of complexity and significant decoding latency. Okay? There is no way around that. So let's go through a couple of definitions. A code word is a block of encoded data. So we'll see more about this when we talk about coding, but at this point, that's all we need to know. So it's a block of data. So let's look at this picture, right? We have here 2 different blocks, and you can imagine there is many of them, right? So this is a block of symbols, okay? And this is a coding block. It means that all these symbols are mutually dependent, okay? So we've taken a block of symbols that we had, and as I say, we'll learn how to do this. And we'll turn it into a block where the symbols are mutually dependent, and there is some redundancy also. Okay? So we have these blocks, and with these dots, I'm indicating that this can be very long. Okay? So a code word is just a block of encoded data. Communication entails the transmission of a succession of code words. I'm going to send one block after another. Okay? So what Shannon showed is that if the rate in bits per second, for example, is below capacity, then the error probability can be driven to 0. So it can be made as small as we want by letting these code words become longer and longer and using the better and better code. Okay? So you have to let the code words grow longer to reduce error probability. But the data rate is not going to 0. So you're just sending more stuff. You just need to have a long string of data on which you can introduce these dependencies. So in practice, what engineers do in designing systems is they make these code words as long as possible, up to the point that the duration, which gives you the latency, essentially the receiver has to wait for a whole block before decoding it. You cannot just start, you cannot just get the symbol and start decoding. You need to wait for the whole block to decode it. So the length of the block is upper bounded by the latency that your application can accept. Okay? So if your application requires short latency, then you have to use short blocks. So this is a limitation that we have in practice. And in fact, there is an issue here that has to be sorted out by the wireless engineer, which is you guys, which has to do with the fact that if we keep the code word short in order to avoid latency, then we may have errors, okay, which means that we may have to resend the data later, which is going to give us even higher latencies. So there's an interesting trade-off between making these code words long or short. So you make them long, so fewer errors, but you have to wait for longer blocks. You make them short, so the block is received very quickly, but there's a bigger chance of an error, and so you may have to resend the whole block later. So there is actually a sweet spot, which is where systems operate, which is sort of optimum in that sense. So for our information theoretic derivations today, we will use no-pass signals exclusively. Everything's going to be in no-pass. And we'll use discrete time signals. So if we had a continuous system, we could just discretize it using sampling, and everything carries over. Okay? We'll always assume, unless something else is stated, that the signals are complex. So we're using both in-phase and quadrature components. And if we chose to use only the in-phase component, then the capacity is the same that I'm going to give you, except divided by half. Okay? Remember that the in-phase and the quadrature are two orthogonal dimensions to signals. So if we choose to use just one of them, for example, for simplicity, then we should use half the capacity. Okay, so everything that I'm going to say for complex signals can be reformulated for real signals, and what you get always is 1/2 the capacity. Okay, so questions at this point? Everything clear? Yes. Yes.
For the coding, once the problems become larger and larger, do we just simply combine different bits from the original bit, or we just add some redundancy to make it become larger?
That's a very good question. Let me repeat it for the CVN students. So the question is, when we make the blocks longer, do we add new bits that we're going to combine to get dependencies, right? Or we add just redundancy, okay? So the answer is we add new bits, because otherwise the rate goes to 0. So if you just add redundancy, you're going back to what I said was believed at the time, right? So for example, an easy way to do add redundancy is to repeat the same message several times, right? So you don't want to do that. So the way you make the codes longer is by taking a bigger block. So the way you create a code word is you take a block of bits. For example, imagine you want to send an email, right? You take your email. You just take the characters, for example, the bytes. You line up your bits. Then you transform this into a block of coded bits, code word, by adding dependencies. So when I'm talking about making them longer, I'm talking about taking bigger blocks of data as input and generating bigger blocks as output. So we want to always add new information as we make the block longer, add new bits on which we introduce dependencies. So we don't want to just add redundancy. We want to add more dependencies. So in other words, the degree, there is some redundancy, but the portion of redundancy is constant as we make the block longer. What we add is more new information and more dependencies. So in the limit, you want every symbol to depend on all the other ones. Okay? But this is a very good point, because if you just have redundancy, then the rate is going to 0, because you're just repeating stuff. And you don't want to do that. That's the old-fashioned. No, that's what you don't want to do. Yeah, but that brings the rate to 0, because repetition, right? For example, if I want to send 1 bit, okay, and I send it using a code of a block of 1 symbol, right? I just send that particular bit, right? I have a certain rate. Depending on, so for example, if that block is, I don't know, 1 millisecond, I have 1 bit per millisecond, right? I imagine I send the same bit twice. I repeat it, right? So I send the bit, and then I send the bit again, right? So I'm sending the same bit. Now I take 2 milliseconds, right? So my rate is now 1/2 bit per millisecond, right? If I repeat 10 times, right, I'm sending 1/10 of bit per millisecond. So you see my rate is going down when I repeat, right? That's not what you want to do. What you want to do is you take, instead of 1 bit, you take 2 bits and send them over 2 milliseconds. So I'm still sending 1 bit per millisecond, but now the 2 bits are dependent, right? I'm going to introduce some dependency. Now I'm going to go to 10 bits over 10 milliseconds. So I'm always sending 1 bit per millisecond, but I'm making these bits dependent. I'll show you how to do that, right? For now, just take that as a leap of faith. In the limit, I'm going to send gazillion bits over gazillion milliseconds. So it's still 1 bit per millisecond. So the rate is not going down. It's constant. But now all these bits have to be made dependent. That's what you want to do to operate close to capacity, right? That's what Shannon tells you that you should be doing. Now that's complicated, of course, because these dependencies, you need like big matrices to create these dependencies. So we'll talk about that when we talk about coding. So for today, we don't want to talk about the details of coding. So let's just imagine these blocks, and we're going to get them to be large enough. Okay? And that's all we're going to know for today. Then in 2 or 3 lectures, when we talk about coding, we'll learn how to construct these blocks. Is that clear? Okay. Other questions? Okay, so let's start with the simplest possible channel, which is the so-called AWGN channel. That means additive white Gaussian noise. And this is something that we don't really see in wireless very much, but it's something that they see in wireline. For example, when you communicate on a cable, so you have no fading. That's why we don't see this in wireless, because we always have fading. Right? But it's a very illuminating setting. So in this channel, you send a signal x of I. So I is the time index. 1, 2, 3, 4. So these are symbols, right? You're sending symbols. This is just a discrete time index. Okay. So you send x of I, and you receive y of I. Okay. So how do they relate? Well, the received symbol is just the transmit symbol times some gain, and G is the gain in power, so the gain in amplitude is square root of G, plus some noise, which is going to be Gaussian. Okay, so N is the Gaussian noise with spectral density n sub 0 and n sub naught watts per hertz. Okay, and we'll call the transmit power P sub t. Okay, so the expected value of x squared, actually x is complex, so it's magnitude square of x. Expectation, this is the power of the transmit signal, is P sub t. I'm calling it P sub t. Okay, and G, as I said, because there is no fading, is a fixed coefficient. Okay, the signal bandwidth is going to be called B, and so the noise power in that bandwidth is n sub 0 times B. Right? N sub 0 is watts per hertz, and B is hertz, and so n sub 0 times B is watts. So this is the noise power. All right? So we'll define now the signal-to-noise ratio, SNR, and we'll call it gamma. And here, be careful. Do not confuse this gamma with the path loss exponent. So these are different variables. We're just reusing Greek letters here because we're out of them, I guess. So I'm just respecting the book's notation. So this gamma has nothing to do with the exponent we are using for the path loss. Okay? This is the signal-to-noise ratio. And signal-to-noise ratio is the ratio between the signal power of the receiver and the noise power. So the signal power of the receiver is P sub t, which is the transmit power, times G, which is the gain of the channel, okay, as you can see here. And the noise power is n sub 0 times B. Okay, so this ratio, which we call gamma, is the signal-to-noise ratio. It's a very important point. Okay? So this formula, which is the capacity of this channel, was found by Shannon himself in 1948 in his first paper, and is probably the most famous formula in all of information theory, says that the capacity of this channel is B times the log of 1 plus gamma. It's a very simple formula, very powerful. And the base of the log depends on the units we choose for the capacity. Okay, so usually we want to express this in bits per second, so we'll choose log to the base 2, but one could possibly choose other bases. But we'll usually use log to the base 2, and so these are bits per second. Yes? Okay, the question is the power should be in dB or in linear scale. Okay, here it's in linear scale, right? It's not in dB. Now, we can express this, and often we will, so this is a good question. Often we want to express gamma in dB, right? So that would be, gamma in dB would be 15 dB, right? Plus 10 dB so we just apply the definition of dB, right? So sometimes we'll be using that, in fact. Just, just don't mix them up, that's all. Any other questions? Yes. Yeah, that's a very good question. If the spectral density should be n0, n0 over 2. The spectral density is n0 over 2 in passband domain, right? And it's n0 in the no-pass domain. Remember, there's always a factor of 2 conversions. So in the passband domain, you have n0 over 2, and you have twice the bandwidth. And in no-pass domain, you have n0. Good point. Other questions? Okay, so let's proceed. Okay, so that's the capacity of this channel. And to achieve this capacity, you have to transmit a signal that is ideally encoded first. What the whole thing, the whole notion of capacity hinges on the encoding with very long blocks. And complex Gaussian also. So Shannon proved as part of his derivations that the signal had to be complex Gaussian. Of course, this is just a mathematical idealization because it is impossible to synthesize a Gaussian signal. But it shows the direction that engineers have to take to construct signals that are good. Can anybody tell me why we cannot synthesize a Gaussian signal? Anybody has an explanation why we cannot? Imagine I want to build a transmitter that sends a Gaussian signal. Right? Could I do that? You guys, come on in. You guys see any problem with Gaussian signals? Okay, so what does the Gaussian PDF look like? Something like this, right? And the tails are very long, right? They go all the way to infinity. So if you have a Gaussian signal, every once in a while the amplitude goes to infinity, right? So you cannot build an amplifier that every once in a while goes to infinity. So it's just a mathematical idealization, but it's a good pointer. And we'll talk about that a little bit when we see digital modulations. Okay, so as we saw, according to Shannon, as long as the data rate, which is signal x of I, the signal transmit signal, is encoded, for example, in bits per second, as long as this rate does not exceed the capacity, codes are sure to exist for which the error probability can be made small and small as the code words become longer and longer. Okay? Conversely, for rates above C, no such codes can exist. Okay? That's the essence of Shannon's result. So Shannon's capacity for this formula we just saw for the AWGN channel applies directly to telephone lines. So in 1948, when he published his paper, modems operated at about 100 bits per second. Imagine the agony of communication at the time. So Shannon's formula, you just plug in the SNR that they had at the time, and it predicted rates of about 30 kilobits per second. So it was initially met with a lot of skepticism and deemed irrelevant because it was so far out. And yet, today, modems operate at 56K, as we know, which is higher than 30K, just because the lines are better. So you just have better lines now, so the SNR is higher. But today, modems at 56K are very, very close to the capacity of the channel. So if you computed the SNR on a telephone line, and you computed that logarithm, you'd find that 56K is just a few kilobits per second away from the actual capacity. So we're very close, and of course, modems involve very complicated coding. Very, very complicated coding is used in modems today to get to this type of rates. So here's a baby example taken from the book for a wireless channel. And it's very baby because there is no fading here. It's just path loss, but just to get a feel for it. So say we have 1 watt to transmit, and we have G is given by a path loss formula, the usual intercept at D0, which is 10 meters, divided by D to the power of 3, which is the graph, because power of 3 here is the gamma exponent, so don't confuse that gamma with the SNR. And a bandwidth of 30 kilohertz, which is what is used in the old, was used in the old analog cellular phones in the United States. And n sub 0 is 10 to the minus 9 watts per hertz, which is a typical bandwidth at room temperature. See, n sub 0 depends on the temperature, which is thermal noise. So this is a room temperature bandwidth. So we plug these numbers into Shannon's formula, and we find that at 100 meters, the SNR is about 33, which is 15 dB. And so the capacity comes to 152 kilobits per second. If we have a distance of 1 kilometer, then the SNR drops to 0.03, which is minus 15 dB. and the capacity drops from 150 to 1.4 kilobits per second. So you can see a little bit how much variation there is going from 100 meters to 1 kilometer with this very baby propagation model. Okay, just to get some feel for how to use the formula essentially. Okay, so we'll start now with fading, but before I'll take questions. If there are any. Right. No questions? Questions? Okay, so you guys, yes.
So, I mean, what you said about the flash band and usually you should keep the SNR at the stereo and the flash band.
Yeah, it's the same. It has to be the same.
So,
Because even if you have factors of two floating, there is both in the signal and in the noise, so they cancel out. Right? So it doesn't matter. The ratio of power of signal to power of noise, even if you both are divided by 2 or multiplied by 2, the ratio is not going to change. So always have to find the, so absolute powers may change, but the ratios, the SNRs have to be the same always. So make sure that you verify that. So you guys want to imprint this formula in your minds, because we'll be using it throughout the lecture today and all of the course. So just keep this in mind, okay? Because we'll be coming back to it over and over, and we'll build on it essentially. So we'll build more complicated formulas using this as a starting point. Okay, so now we'll start with fading channels, which is what we find in wireless, and which is unfortunately much more complicated. So we'll start simple, and we'll start with flat fading. Okay, so narrow band channels, flat fading. So it's a very similar formulation as we had before. The only difference is that now the gain itself is a function of time. Okay, so before we had a fixed gain, G. Now gain, G is a function of I. So it changes from symbol to symbol. And as we know, it can be modeled as a random process. So we'll always assume that this random process is stationary and ergodic, okay? Which are very valid assumptions. And its distribution depends on the class of fading. For example, we can have, if the fading is Rayleigh fading, then the G will be an exponential process. It can be also Ricean or Nakagami, the usual distributions, okay? Now, computing the capacity of fading channels requires some idealizations of the fading process. And in order to get meaningful results, one has to go through this. So there are two idealizations that are that are used in practice, and that we're going to be using as well. So the first is called sometimes called the ergodic idealization. So in this idealization, we'll assume that the channel varies widely and ergodically over the duration of a code word. Okay, and I'll show you a picture in a second. That's going to help. So just keep that in mind. Now we'll see a picture. In the second, let's go to the picture. Okay, so keep this in mind, right? You have a block. We saw this before. We have a block of data. So these are all blocks of these are code words. Okay, and we have an ergodic channel. So something like this, something that changes. And within a block, within a code word, there is a lot of change. So we get to see all the values of the fading process with their corresponding probabilities over a single block. Okay, that's the ergodic idealization. So that's typically what you find at high speeds, so in fast fading channels, to find this situation. Now at the other extreme, we have what's called the quasi-static or block fading channel, where things change very slowly. So this would be a fast fading channel. Now look at the slow fading channel, which will be this, right? This is a slow fading channel. So imagine you take that channel and you stretch it out. So reduce the speed, stretch it out until you get something that's almost flat, like this. Okay? Now within a code word, there is very little variation. Okay? So that's the quasi-static channel. And the idealization is further pushed in the sense that we usually will assume that the fading is constant during one of these blocks. And then it changes, for the next block it changes. Okay, so exactly in the transition of the blocks, it's going to change. Okay? These are all artifacts that allow us to do analysis and get interesting results. and take them with a grain of salt. But they're very useful because they allow us to get a lot of insight, which is actually very applicable. So keep in mind these are idealizations, but they're useful. Okay, so let's go back here. Exactly. Okay, so we have this idealization. For fast-fading channels, we have this ergodic idealization, a lot of change in each code word. For slow-changing channels, we have this quasi-static or block fading model where the channel is about constant for a block, one of these coded blocks, duration capital T. And then it will change for the next block, and then for the next block, and so on and so forth. So it moves like a staircase kind of thing. Okay, so since the fading is frequency flat, G, the gain G is just a scaling coefficient. There is no ISI distortion. And since this gain changes over time, the capacity turns out to depend critically on what we know about G. Okay, so the knowledge of G is called CSI, channel state information, and nothing to do with the TV show. What is it called? Anybody here? Crime scene investigation, right? Which I've never seen, but I heard it's good. So nothing to do with it, but it's the same acronym. Channel state information. And this is very important. So there's a lot of processing in your cell phones that whose job is to estimate the channel and obtain this CSI. Okay, very important. And we'll see in the lecture why this is important. So we're going to consider 3 different scenarios, or 3 different levels of CSI, if you will. So the first is called CDI, which stands for Channel Distribution Information. So in this scenario, transmitter and receiver know the distribution of this random process G of I. Okay, for example, if they know its mean, its correlation, and all that stuff. If they know if it's Rayleigh fading, or Ricean, or Nakagami. But they do not know the actual value. So this is a random process, random variable, you can take it. And we don't know the exact value. We just know that it's taken from a distribution that has certain characteristics, statistics that we know. For example, if it's Rayleigh channel, we know it's Rayleigh. We know zero mean in complex Gaussian fading process with some correlation, blah, blah, blah. But we don't know the actual value. We only know the distribution. That's the CDI. Then there's a second scenario, more refined, which is the receiver CSI. So in this case, the receiver actually knows G at all times and tracks it. And actually, this is what your cell phones do. All your cell phones track G at all times. So this is a very important case. Okay? So in this case, the transmitter knows only the distribution. The receiver knows both the distribution and the actual value, G of I. This is the most interesting case in practice in terms of how systems actually work. There's a third case, which is also applicable sometimes, which is called transmit and receive CSI. So in this case, both transmitter and receiver know the value G of I. So here, everybody knows everything. Both know the distribution, and they also both know the actual value. Yes? Yes, the question is receiver CSI is open loop and called open loop, and the other one is called closed loop. The answer is yes. That's exactly right. It doesn't have a name. It doesn't have a loop name. So open loop and closed loop is terminology that is very used in like standardization, and so if you go to the standard documents, that's usually how these scenarios are referred. And this one doesn't have a loop name, also because this one actually is not really implemented in practice. So these are the two that are pertinent to actual systems, like the ones that you guys use. Okay, so these are the 3 scenarios. We'll study the 3 of them today. And I note here that with fading, the SNR gamma is also a function of time. Okay, so gamma now is also a function of I, because G is a function of I. So now gamma at time I equals P sub T, the transmit power, times G at that time instant I, divided by the noise power n sub 0 times B. Okay? So first case, and now we'll see why this case is not so interesting. Capacity with CDI, unknown. So this may amaze you after 58 years of information theory, but this problem has not been solved yet. So typically what happens in these capacity studies is that the less CSI, the harder the problem. And in this one, there is very little CSI. There is only distribution information. And it's very hard to study, so hasn't been cracked yet. This points to the importance of having at least receiver CSI, which is why all the systems that we have today estimate the channel to obtain receiver CSI. Okay, so that's all I want to say about this. It's a very hard problem, hasn't been cracked. The channel has a capacity, we just don't know what it is. So let's move on and talk about the receiver CSI case, which is a very interesting case. So in this case, G of I, and therefore also gamma of I, are known by the receiver, but not by the transmitter, only the receiver. Okay? Now, see, the transmitter doesn't have CSI, it doesn't know gamma, G or gamma. It must choose a data rate without knowing gamma, right? So imagine you're the transmitter, right? You know the channel is rarely fading, for example, with a certain variance and correlation and mean. But you don't know exactly what's going to be at this point in time what you want to communicate. So which rate are you going to send? You have to make a choice without knowing the actual channel, if the channel is going to be good or bad. That's a difficult problem, okay? So we'll see how that's tackled. So there are two notions of capacity, and here we come back to these two idealizations. Remember, we had this ergodic regime for fast fading channels, and we had this quasi-static channel for slow fading. Okay, so each one has a different capacity notion, if you will. The first one, for the first one, we talk about channel capacity or ergodic capacity sometimes. Applies when fading is fast, so that each code word is affected by many different values of the fading. Okay, remember the picture we saw. Okay, here it is. So this scenario. That's called the Shannon capacity or the ergodic capacity in homage of Shannon. For the other one, we have what's called the outage capacity. So this applies when the fading is slow, and it's about constant for each code word. And then it may change from code word to code word. All right? So again, we find that capacity exists for more general fading conditions, but it's just not easily computed. Yes?
Your ergodic capacity is much lower than the
The question is if the ergodic capacity is much lower than the outage capacity. Well, why do you say that? Have any particular reason in mind?
the average capacity is 10% of the time.
This is a very good discussion. So let's defer it for a little bit. And so we go through the definitions, and we'll come back to it. So it's a very good question. Like which one is bigger and why? So we'll come back to it in maybe half an hour. So I was saying that, yeah, so when the fading is not idealized in these extreme cases, in these limiting cases, the capacity is still well defined. It's just harder to compute. So that's why we use these idealizations. Okay? Because we want to get some insight and some understanding. Okay, so we've seen this already. These are the pictorial representation. Okay, let's start with the Shannon capacity. Okay, so we are in this top scenario. We have this type of fading over the code words. Okay, so the pertinent notion is the Shannon capacity. And the Shannon capacity is, in this case, easy to compute. Okay, remember that we saw that the capacity for an without fading was this, right? Now we have fading, so one can actually prove that what you do is you say, okay, at time I, so you can visualize it this way, right? At time I have a capacity that's given by this, right? At time I, this is the capacity of a channel of that SNR. So the Shannon capacity, because because the fading changes so much about the code word, is actually meaningful to what you get effectiveness and expectation. Okay, what we get effectiveness is a time average. So you get to average over time, because the code word is going to see all these different changes. You get to average this over time. Okay, so you take this for each time I, and you average it over time. Okay, and that gives you the capacity. Now, because the channel is ergodic, the temporal average is equal to an expected value. Remember, this was the key property of ergodicity, that temporal averages are equivalent to statistical averages. So we get an expectation. Okay, so all we have to do is take this guy and expect it. Okay, expect it over the distribution of gamma, and that is the Shannon capacity. Okay, is that clear? Does that make sense? So we're just taking, so the temporal variation in this case due to fading is just giving us an averaging. That's all. Now, this is an easy result, doesn't mean it's easy to prove. So we're not going to get into the proof. But it's a very nice result. Now, let's play with it a little bit. There's something called Jensen's inequality that says that for a concave function, okay, so you guys know what a concave function is, right? So this is a concave function, and this is a convex function. Okay, so the second derivative is negative, second derivative is positive. Okay, so for a concave function, we have that it can be shown that the expected value, okay, right. This is bigger or equal, right? Where's it equal? Okay, so if f of z, so this is a function defined on z. Let's imagine that this is z, and this is f of z. So f of z is concave, its second derivative is positive, negative, I'm sorry. The expected value of f of zeta, z, is greater or equal than f of the expected value of z. So in other words, if we bring the expectation inside the function, we get a reduction. Okay, that's what this says. Taking the expectation inside the function implies a reduction. For a convex function, we have the converse. So expected value of f of z is bigger or equal so for a convex function, the expected value of f of z is bigger or equal than the function f of the expected value of z. So in this case, bringing the expectation inside the function entails an increase. Okay, and if you want to think about this, what this says is that the chord between 2 points is always below the curve. And here we say that the chord between 2 points is always above the function. So graphically, in other words, you can turn these geometrical facts, right? Any 2 points, the chord is always below the curve. This is equivalent to this, and vice versa. I don't want to spend more time on this, but if any of you have doubts, you can come to us, ask me about this on the break, for example. So we're going to use these now and apply it to our newly found capacity formula. Okay, so let's take this expectation and bring it inside the logarithm. Now the logarithm happens to be a concave function, right? I don't know. So the logarithm, right? The logarithm moves like this, right? This is z. It's log of z. So the logarithm is a concave function. So we can apply this inequality, and we take the expectation, bring it inside, and we get a reduction. Okay, so we have that C is less or equal than B times the log. So I expected, in other words, I bring the expectation inside, so I have the expectation of 1 plus gamma, and that's 1 plus the expectation of gamma. Okay, so I end up with this, where gamma now is the expected value, gamma var is the expected value of gamma. Okay, so you already followed this step, this bringing the expectation inside and applying this inequality. Questions here? Yes. Go ahead.
So gamma bar is basically saying that it's always going to be less. Gamma bar is basically the curve. You're saying that it's always going to be big. Gamma is always going to be less than this value.
No, C. So gamma. Okay. So gamma bar is just the expected value of gamma. So gamma is gamma of I is the SNR at time I. So this is the average SNR, right? So what we show, so with this exercise, what you can show is that, okay, so let's define gamma bar as the average SNR. Now imagine that we have a channel with no fading, right? Magically, we did away with the fading. And we got, instead of a time-changing SNR, we have the average SNR. For example, we go here. And this is a very good question. So we go here, we say, okay, so let's say we can equalize this channel and have it be constant at its average value. Now, what's the capacity of that channel? Well, it's log of 1 plus gamma bar, right? There's no fading, that's the capacity of the channel, right? Now, what we've shown here using this inequality is that the capacity of this channel with fading is always less than the capacity of an equivalent channel with the same average SNR but no fading, right? So in other words, I'm saying, if I could turn this fading and just flatten it out, right, with the same average. So for example, I push the power, I increase the power here, reduce it here so that it's flat, but the average is the same, okay? That's some magical channel which has the same average, but no fading. That channel would have more capacity than the fading channel. Right? The channel, which has this capacity, log of 1 plus gamma bar, would always be better than the actual fading channel.
So would it be better to find the minimum value of the fading channel?
The fading channel has a value given by this expectation.
Yeah.
Right.
You're saying, and what you're saying with the gamma bar, you're able to say this is the actually bound. The channel we actually have another better.
Yes, that's exactly right. So we can. So this is an upper bound, in fact.
Yes.
Right.
So wouldn't it be better to find? Well, I guess the lower bound.
The lower bound, well, you can find better lower bounds, but one lower bound will be 0, right? So you can say that the capacity is always going to be between 0 and this value. That's one observation to make. But the other one is that fading. The point that the professor wants to make here, Professor Goldsmith, is that fading is detrimental, essentially, right? So if you could have the same power, the same average power, with no fading, it would be better. So even though fading, you get to average over time, right? You don't get back to the point that there was no fading, right? Because one may be tempted to think that, okay, so I have a temporal average here, right? So even though the channel is fading a lot, because I'm going to average it, I get to the same capacity I would have if there was no fading. That's not true. So even if we had no fading and the same average SNR, the channel with fading is worse off. And the reason is that we don't get to average, look at this formula, you don't average the SNR, you average the log of the SNR. And this inequality, Jensen's inequality, tells us that averaging a concave function is worse than getting the concave function of the average. So in other words, the log of 1 plus the average SNR is better than the average of the log of 1 plus SNR. So the point here is that besides the fact that you do get an upper bound, which is true, which is actually useful sometimes, is upper bound, because it's firmly tied, so it is a useful bound. But the other observation is that fading is in general detrimental in this scenario. And let's go through an example. So say we have 10 milliwatts of power. We have a bandwidth of 30 kilohertz, and the noise density is the usual, 10 to the minus 9. You'll see this number on watt. 10 to the minus 9 watts per hertz. And just to make it very simple, let's consider a discrete fading that takes only 3 values, okay? So that we don't get any nasty integrals. I think this will help clarify this point, going through this example. So let's take the time. So we have a channel that takes 3 values only. So G takes 3 values. Okay. Okay, 10% of the time, G takes the value 0.05. Okay, so G, let's call this G1. 10% of the time, G is equal to 0.05. Okay, so this means that gamma is equal to P sub t times G divided by N sub 0 and W. Okay, so anybody has a calculator handy? Okay, well, I can do it. So we have 0.83. Okay, you have the book, no? Is it in the book? Okay, good. Oh, perfect. Okay, so you can tell me the values. 0.83, right? Okay, hold on. And then this has now the log of 1 plus gamma 1. So the log of 1.83. Sorry, times b here. So this is what? 26.3 kilobits per second, right? Okay. Now, this is the first value taken by the channel. The second one is 0.5 taken with 50% probability. So 50% of the time, the channel takes a value, let's call it G2, 0.5. And this corresponds to gamma 2 of? Yeah, of course, 10 times. Of course. And b times the log of this, log of 1 plus this. .191 point something, no? 0.9 kilobits per second. And the last value taken with 40% probability. But this example, by the way, is in the book, so is 1. So gamma 3 is equal to 1. Sorry, G3 is equal to 1. So gamma 3 is equal to, anybody? Gamma 3? No, this is 333, right? Is it 333?
Yes.
Remember this one. And this is? Log of 1 plus this? Anybody has a hand? Okay. Okay, so this is what we have. So the channel, remember, the receiver knows G and gamma and everything. The transmitter doesn't. It only knows the probabilities. And these are the 3 values taken by the channel. So now, let's start by computing the ergodic capacity. So we apply this formula over here. We take the expected value. So we just have to average these 3 values, right? We take these 3 values and do the average. Yes. Yeah, it would appear.
But at that point, shouldn't gamma 1 be gamma 2 be times gamma 1?
Yeah, it is 10 times. 0.05, hold on. Can I get a copy of the book, anybody? 0.05. Can I borrow a copy of the book from somebody? Okay, it's in page 104. 0.83, that's correct. Okay, so I see what the problem is. These are not g's, these are square root of g's. Okay, sorry guys. So that's the problem. You have to square these. Okay, so now everything works out. Okay, so to compute gamma, you have to square this times 10 milliwatts divided by the noise power. Okay, thanks. Okay, so everything is correct. So now, the first step is to compute the ergodic capacity. And thanks to this very nice formula, that just boils down to an average. Okay, so we take these three rates, 26.3, 191.9, and 251.5. We add them up, divide by 3, and we get 199.2. Okay, about 200 kilobits per second. That's the ergodic capacity. Yes. Yes, I'm sorry. Thank you. Yes. It's not just adding up and divided by 3. So you take this one times 0.1 plus 1 times, yes, thank you very much. Sorry about that. They have to be weighted by the probabilities. And that gives this 199.2. Okay? So that's the ergodic capacity we have up there. Now, the average SNR is obtained by averaging the 3 SNRs, 3 gammas, again in the same way. So the first gamma times 0.1 plus the second gamma times 0.5 plus the third gamma times 0.4. And that comes to 175.1, which in dB is 22.4. Okay, right here. So what would be the capacity of a channel with no fading and this average SNR? So we take log of 1 plus 75.1, and that comes down to 223.8 kilobits per second. Okay? So as you can see, our fading channel has, which is this 199, has less capacity as expected than a corresponding channel with no fading at the same average SNR. Okay? So that's the point. Now, one could say that in this case, because of fading, we're losing, what is it, about 24 kilobits per second, which is about 10%. So in this case, one could argue that fading is costing us about 10%, which is not too much in this case. Yes? Yes. So the question is, if this notion of capacity is used for fast fading, and the answer is yes, because to get this expectation, which is to get this time average, you need to be in this scenario where this average is meaningful. So this average comes from all these variations. Exactly. Yes, and that's what's called the channel capacity. Right.
A lot of times you'll have error in the perception because you were sensitive over there's got a capacity of 199. A lot of times
yeah, so the question is what happens when the SNR, for example, on one of these fades, right? It's one of these SNR. The answer is that the capacity only makes sense when applied to the whole block. So capacity is not meaningful for one symbol. Remember, capacity has to do with long blocks of coded data where everything is dependent. So even if one of the symbols, and in fact it will happen, right? Like here or here, these symbols are received with very little power. So essentially they're going to be lost. Doesn't matter because the capacity tells you that as long as you don't violate the capacity, the whole block will be decoded without errors. Because some of the other symbols are going to be very good, and because they're all dependent, and they're all redundant, mutually redundant. So the good ones will allow you to recover the bad ones. That's the beauty of coding. And so as long as the rate of the whole block in bits per symbol is below this capacity, the whole block will be decoded with no errors. That's a very impressive result. So that's why Shannon's result was so hard to, at the time, for people to accept. It took years for people to, at the beginning, people didn't believe that this was true. But it is. So that's the key, right? Coding, by making all these symbols mutually dependent, you can make sure that the good ones help the bad ones. And so the whole block won't be decoded with no errors, as long as you stay below capacity. Okay, very good question. Okay. Okay, guys, I think that it's time for a break. So let's reconvene in 15 minutes, okay? We studied this ergodic regime where we have all these, a lot of channel fading variations within each coded block. And we found that these variations give us an expectation. Okay, we went through an example. And now we'll study the other setup, okay? So we go to slow fading channel where the channel is about constant for each block, okay? So in this setup, the notion of capacity that applies is the outage capacity. And as I said, in this case, G of I and so gamma of I as well remains constant for many values of I. Remember that we need the channel to be about constant for each block, and with each block to be very long. That means that we need the channel to be constant for many symbols. Okay, so this idealization requires that the channel changes very slowly. Okay? The outage capacity departs from the usual notion of capacity because errors are actually allowed. So we're going to allow for outages, which means we're going to allow for errors. So that, in some sense, violates the original notion of capacity, which was to quantify the rate at which you can transmit with no errors. So here we're going to allow for some errors. Recall that we have this interesting dilemma, right? The transmitter has no CSI, so it does not know gamma of I. Yet, it must choose a rate without knowing gamma of I. So the transmitter doesn't know, so imagine you're here, right? The transmitter doesn't know the channel is going to be down or up, good or bad. It has to choose a rate. So the only choice is to make a guess. So we're going to choose a rate. So we're going to choose a gamma min that we hope for, and we'll transmit at b times log of 1 plus gamma min. Okay, so we're going to go with this rate, and then two things may happen. The first thing that may happen is that the actual gamma is bigger than gamma min, or and is equal, and so the data can be decoded correctly, because the rate we chose was below the capacity. Okay, so that's one possible outcome. The other outcome is that the actual gamma of I is smaller than gamma min, the gamma min that we chose, and so the data cannot be decoded correctly because we chose a rate that was too high, so we exceeded the capacity. So in that case, we say that an outage has occurred. Okay, so these are the two possible outcomes when we choose a rate b times log of 1 plus gamma min. The outage probability is the probability that gamma is smaller than gamma min, and that's what we call p outage. Remember that we use the same notation in the propagation material when we talk about outages. And so when we find now something called the throughput, which is the average rate correctly decoded. That means that we're going to count only the bits that are decoded without errors. Okay? So what's the throughput? Well, we chose this rate, right? We chose, we sent the rate b times log of 1 plus gamma min. And p out, with probability p out, the information is not decoded because there's an outage. So with probability 1 minus p out, the data is decoded correctly. And so the data that goes through is 1 minus p out times b log of 1 plus gamma min. Okay? So that's the successfully decoded data per unit of time, and that's called the throughput. So another dilemma we have is the choice of gamma min. So gamma min or C, which is this log of 1 plus gamma min, is a design parameter that depends on which kind of outage probability we can accept. So if we want few outages, we have to choose a very small gamma min, right? We have to use a very conservative rate. If we can allow for more outages, we can have a more aggressive rate, and so a higher gamma min. And in order to maximize the throughput, I'm using the term C out to denote the throughput. That's because of outage, C out, a capacitive outage. So to maximize C out, we have to optimize the gamma min, and there is an optimum gamma min that we can find that gives us the maximum C out. So typically, the outage capacity is represented graphically by a plot of b times log of 1 plus gamma min as a function of P out, which is the probability that gamma is smaller than gamma min. So in the book, we have a case of this plot for a rarely fading channel in figure 4.2. Here it is. So this is a plot for rarely fading. This is C divided by B. So this is just log of 1 plus gamma mean. Okay. This axis is plotting the log of 1 plus gamma mean, and this axis plots the probability that gamma is less than gamma mean when the fading is rarely. Okay, and we have this typical shape. So if we want a very small outage, we want to be down here, we have to use a very small gamma mean, so a very small rate. This is the rate. And if we can allow for higher outages, we can choose a higher rate, right? For example, imagine I tell you, okay, we can allow for 1% outages. So 1% of the blocks, of the coded blocks, can be lost, but we want to recover 99%. Where can we operate? Well, 1% is here, right? 10 to the minus 2. So we can operate at about, I would say, 1.2. So log of 1 plus gamma mean can be about 1.2. Okay, that's how you read this type of plots. Okay, so let's see an example. And in fact, all these examples we'll be using today use the same channel, this baby channel with 3 states. That's because it's very easy to compute. So we'll come back to the same channel. Remember, the bandwidth was 30 kilohertz, and gamma equals 0.83 with probability 10%. It equals 83.3 with probability 50%, and it equals 333.3 with probability 40%. Okay, so we want to find the graphical representation. So the plot that I just showed you, that was for rarely fading. We want to find the same plot for this channel, and then we want to find the outage probability at different values. The throughput for different outages. Okay, so let's do that. And since the SNR takes discrete values, the representation is going to be a staircase. Okay, it's not continuous; it's discrete. So it takes only discrete values. It has to be a staircase. So let's build our plot, right? And fortunately, we still have the data here on the board. So if we transmit at a rate of b times log of 1 plus 0.83, okay, there will be no outages, right? Because gamma, we have 3 possible gammas, and gamma is always bigger than 0.83, right? So it doesn't matter which of these values it takes. The 3 values exceed 0.83, right? The first one is 0.83, the second one is 83.3, the third one is 333. So the 3 of them are equal or larger than 0.83. So this rate can be sent with no outages. Is that clear? You guys see that? Right? The channel is never going to be bad enough that this rate doesn't get through, right? So below this rate of 26.2, there's no outages. That's why we are all the way up to this rate. The outage is 0. Okay, so we're over here. Now, say we transmit at a rate of b times log of 1 plus 83.3. In this case, we'll have outages, right? Because when the channel takes this value, 10% of the time, it's going to be too bad to support this rate, right? Because the gamma is too small, and so the rate we can support is 26.3, which is smaller than what we're trying to send. So when we send this rate, which is 191.9, we'll have 10% of outages. So the throughput is going to be okay, forget the throughput. We'll talk about that later. For now, we just want to do the plot. In the next slide, we'll compute the throughput. So at this rate, we'll have 10% outage. Okay? So 10% outage over here, all the way up to this rate. Okay? Now, if the rate we send is b times log of 1 plus 333.3, which is about 251 kilobits per second, we have outage with probability 0.6, right? Because in this state, we're in outage. In this state, we're in outage, right? So these are 10 plus 50, 60%. So only here we'll be able to communicate. In these two states, we'll be in outage because our rate is too aggressive. So at this rate of 251, we are over here, 60% outage. Okay? And if we transmit above 251, we have 100% outage, right? Because it doesn't matter where the channel is. The biggest rate we can support is 251. If we transmit at 260, for example, or 300, the channel can never support that rate. Doesn't matter. The T states are too bad. So above this value, the average is equal to 1. Okay? So this is the kind of plot you get for this T-state channel. And here I'm just summarizing what I just said. If we transmit out of below 26.2, there are no outages. And so the throughput is exactly 26.2. Okay? If we transmit between 26.2 and 191.9, so if we transmit here between these two, we have a 10% of outage. Okay? So the throughput is 1 minus 10% is 0.9. So the throughput is 0.9 times 191.9, which is 172.75. So that's the throughput, right? We're losing 10% because of outages. Now, if we get more aggressive and we transmit at between 191.9 and 251.5, so if we operate over here, we have 60% outage. Okay? So the throughput is 0.4 times 251.5. It's the maximum value, which is 125.78. Okay? So that's the throughput. So those are the possibilities. If we transmit above 251, as I said, no data is decoded. We're always in outage. So we have 0 times 251 is 0, so there is no throughput. So the best throughput is clearly obtained by transmitting at 191.9 over here, which is going to give us a outage probability of 10%. Okay, so the best point for throughput is right here, this corner. We have 10% outage, but the throughput is the largest we can obtain. So if 10% outage is acceptable, then that's a solution. Okay. Now notice that the blocks that are in outage may have to be resent later. Usually that's what we do. So so this might incur additional latency. So it may be the case that you have an application that cannot tolerate latency, for example, gaming, for example. And so what you do is you back off on the rate and you transmit at 26.2 so that there is no throughput. So you go back to this corner. So here is the optimum point for throughput, but if latency is a constraint, you may have to go down to this point, where you only have 26.2, but you have no outages. Okay, so those are design constraints. Okay, is this clear? Example. Because that's the end of the section on receiver CSI. So that's all I want to say about that. Now we'll get into the section where we have transmitter and receiver CSI. So time for questions? Yes.
The receiver CSI, that's typically the using cell phones.
Yes, the receiver CSI is always, the question is if the receiver CSI is what's using cell phones. And the answer is yes. Most systems, I mean, all systems that are in use today use receiver CSI. So there is an estimator in the receiver that tracks the fading. There is something called there's a PIMO channel that's used just for the purpose. So the receiver is always tracking the fading at all times and using that information. Now, in some systems, there is a certain amount of feedback to inform the transmitter of the CSI, and which is what we're going to tackle in the next section. But that can only be done at low speeds. So when you move too fast, there is no time to just send the information back. So I would say this scenario is the most practically interesting. Yes.
When you say that we have an error, when you lose data, we're losing the entire code.
Yes.
We our code will try to all belong. It's not data.
Yes. Let me repeat the question. So the question is, when there is an error, you may potentially lose the whole block. And the answer is yes. Yes. If the block is in error, you have to discard the whole block and resend it. So you want to do that as little as possible. Exactly. So we'll talk about this a little more when we deal with coding. But yeah, this is a good point. So it's not that you just lose one symbol, for example, because often what the problem you have is that you don't know what the error is. So the receiver is able to detect that there has been an error, but it doesn't know what the error is, so it cannot correct it. Usually you can just detect that there has been an error. There is a verification, so that there's a way to verify if there's an error, but you cannot correct it. You have to resend the whole block. So it is a problem, and it should be done. It should be avoided as much as possible. That's why you want to try to avoid errors. So this is a very good question. So that's why, even though here the throughput is maximized in this point, right, with 10% outage, the delay of resending these 10% of packets may be such that you may actually want to back off and avoid doing that. It's exactly the point of this example. Very good question. Other comments or questions? Okay, so let's move on. And I will deal with the case where there is CSI at both receiver and transmit. Okay, so the dilemma we had in the previous section of how to choose the rate, we don't have it here, right? Because since we know the channel, we can choose exactly the right rate, right? So we don't have this problem of choosing a rate without knowing gamma. Now we know gamma. So we can choose exactly log of 1 plus gamma as the rate. Okay? So things are much easier here. And as I said, the more information, the more CSI, the easier it is to communicate and to compute the capacities. So there's another advantage of knowing the channel at the transmitter, which is that we can do power control over time. So what do I mean? Well, imagine that the limitation in your cell phone comes from a battery, right? So you have a finite amount of energy that you can store in the battery, and you want to use it efficiently. So you may say, now all of a sudden we know the channel, right? The transmitter knows exactly where it is in the channel. So if you're in a bad channel moment, you know that, right? So you may say, okay, I'm right here in a really bad spot. So I'm not gonna burn any power because this power is gonna be wasted. I'm gonna send something and it's gonna be lost because of fading. So I'm not gonna send it. I'm gonna keep that power and I'm gonna use it when the channel is better. Right? You can do that. But you need to know the channel. And now we know it in this section. So knowledge of the channel at the transmitter allows you to do this power control, it's called, power adaptation. So we're going to be looking at two different strategies. First one is to send constant power, P bar. The second one is to adapt the power over time based on the channel with the same average, P bar. Okay, so the structure looks like what is shown in figure 4.3. So now you have an encoder that encodes the data into blocks, and then you have a power control that adjusts the power based on channel information, which comes from the receiver. Okay, so the receiver is estimating the channel, gathering the CSI, then relaying it back to a feedback channel, and now this guy now is adapting the power on the basis of this information. Okay, and now here's the fading and the noise. So that's the idea here. And let's start with the easiest case. So let's say that we don't want to do that. Let's say we don't want to do that. We just send the constant transmit power P bar, maybe for simplicity, because the amplifier doesn't allow us to do power control. So then the capacity is exactly the same we had before. The channel capacity is the same. So it's the same expectation. And the reason is that if we don't adjust the power, even though we have this information, we're not using it. So we know the channel, but we're not using it, this information, so we get the same capacity. It's the average of B times log of 1 plus gamma. Okay? So the observation here is that transmit CSI does not increase capacity unless we adapt the power. So let's do that. Let's adapt the power as a function of the CSI. So now instead of P, constant P or P bar, we'll have P of gamma. Okay? So now we'll adapt the power on the basis of the fading. So when the fading is good, we'll do something. When it's bad, we'll do something different. With the constraint that the average power over time, and since we have ergodicity, that means the expected value of the power is equal to P bar. Okay? So we have the same power averaged over time, and now we're going to distribute it temporally on the basis of the channel information that we have. Okay? So now, with constant transmit power, the SNR was gamma. No? With adaptive power, let's find the SNR that we have. So we had gamma equal to PT times G divided by N0W. Okay, remember this was the SNR with constant transmit power. Now the power is a function of time or function of the channel state. So we have this, right? We have P of gamma times G divided by N0. Right? So it's the same thing, but now the power depends on gamma. And we can write this, as you can see, as gamma divided by PT and times P of gamma. Okay? So that's clear, right? We take this guy divided by PT, multiplied by P of gamma, and we get our new SNR. Okay? So with power adaptation, the SNR is P of gamma times gamma divided by P bar. Okay? Notice that besides the power, we need to adapt also the rate, and so the coding and decoding strategies, which is another complication. Now, what's the capacity when we're adapting the power? Okay, here things get a little more involved. So this is the formulation, right? As always, we have B times log of 1 plus gamma, and now gamma is P of gamma divided by P bar, right? So we have log of 1 plus gamma divided by PT times P of gamma. Okay. This is the basic ingredient, right? It's, as usual, B times log of 1 plus gamma. And that's what we have over here. PT is P bar, sorry. Change the notation here. Okay. So that's as usual the key ingredient in formulating the capacity. Now, this integration is just the average, right? This is the PDF of gamma. So this is just an average. This integral is just an average. Now, P of gamma, in some sense, is telling us which strategy we're using to adapt the power, right? How do we adapt the power? A function of gamma. So there's an infinite number of ways in which we can adapt the power based on gamma. So of all these possible strategies to control the power, we want to choose the best one, right? So we want to maximize this integration over all the possible P of gamma strategies, satisfying the fact that the average power is equal to P bar. Okay, so we cannot violate this condition. This is the power we have. The average power has to be equal to P bar. But within the class of strategies that satisfy this condition, we want to find the best one, the one that maximizes this integration, this expectation. So that's the formulation. So we have to solve this problem to find the capacity. Is this clear? Anybody has a doubt? Okay, so we have the usual expectation, and now we want to maximize it over all the possible power adaptation strategies. Now, how do we solve this? This is an optimization problem, somewhat involved, and it can be solved using Lagrangian techniques, which are beyond this course, so you don't need to concern yourselves with the details, but some of you might have seen that before. Anybody has seen Lagrange multipliers here before? No? Well, yeah, I know you do. Anybody else? No? Okay, you'll probably see that if you go into graduate school. So, we don't need to concern ourselves with the details. I'll just briefly sketch it. So when you have a maximization with a constraint, what you do is you build a new variable called the Lagrangian. Let's call it L, which is equal to the same function we want to maximize, which is this integration. And now we add another term, which is this one. So you build a new function. So you want to maximize a function with a constraint. What you do is you build a new function and you build a constraint into it. And then you take the derivative and set it to 0. And that way you find the solution. So what you find if you apply this is the following. You find that P of gamma divided by P bar is equal to this function. So the answer, even though the problem is fairly involved, the answer is surprisingly simple and very nice. And it's this. You want a strategy that behaves as follows. You want to have something called the cutoff SNR, which is gamma 0. And I'll show you now how to calculate it in a little bit, okay? But for now, we just call it the cutoff. And forget this formula. We don't need this. Okay, so forget this. We'll have a cutoff, gamma 0, okay, which will compute. So whenever gamma is below this gamma 0, so when the channel is bad, essentially, right, bad enough that it's below this gamma 0, we're going to send no power. Okay, so the idea is when the channel is bad, we'll save the power for some other time. So when the channel is below gamma 0, we'll send no power. So P of gamma is equal to 0. That's pretty intuitive, right? When the channel is good enough, so it's at least equal to gamma 0 or better, then we'll send power. Now, how much power? We'll send exactly 1 over gamma 0 minus 1 over gamma. Okay, that's the rule. So that's the solution to this problem. Okay, and now I'll show you in a little bit with some pictures what this looks like, because this is a very famous optimization. Okay, but for now, this is what you want to memorize. Remember, when the channel is very bad, we just turn it off. We don't transmit. When it's decent or good, we transmit, and the power we transmit is 1 over gamma 0, which is some constant, minus 1 over gamma. Okay, so the better the channel, the more power we send, right? Because better channel means higher gamma, right? Which means that 1 over gamma is smaller. So the better the channel, the more power we send. So essentially, this strategy, which is optimum, says that you should send more power when the channel is good, and little or no power when the channel is bad. It makes quite a lot of sense to me, right? Yes. Yeah. Okay. So this is lambda is the lambda over here. So it's part of the Lagrange. It's called the Lagrange multiplier. So we won't get into it, so don't worry about it. I just put here, it's in the textbook, so I wanted to bring it to your attention, the fact that it has nothing to do with the wavelength. It's a completely different variable. It's part of the optimization. And you don't have to worry about it. Okay? Other questions? Okay, so now that we have, just hold on to your horses because we'll build on this over the next few minutes. But now, using this strategy, what's the capacity? Well, we take this guy, we plug it in here, right? Essentially. So we want to have 1 plus P of gamma times gamma divided by P bar. So let's look at that. We have that P of gamma divided by P bar times gamma is equal to all right. So I multiply this equation by gamma, both multiply this by gamma, and I'm finding that P of gamma times gamma divided by P bar is equal to gamma divided by gamma 0 minus 1. Okay? So 1 plus this, 1 plus P of gamma divided by P bar is equal to gamma. So think it's very simple, right? 1 plus that is just gamma divided by gamma 0. And so we have the log of gamma divided by gamma 0 times V. And now we have an integration from 0 to infinity, but what happens is that when gamma is less than gamma 0, we send no power. So to account for that, we truncate the integration, and instead of starting at 0, we start at gamma 0. Okay? So for gamma below gamma 0, we turn it off. So we just truncate the integration, and that's the capacity, is this integration. Okay? Questions? Can you all see how you take this solution, you plug it inside of this integration, and you get this answer? More or less? Okay. Now, this is a function of gamma 0, not this. So now, how do we find gamma 0? Right? That's the key parameter here, gamma 0. How do we find it? Well, we have one more condition to impose, right? The average power has to be equal to P bar, right? So, in other words, the integration of P of gamma times little p of gamma times d gamma is equal to, right? The expectation of P of gamma, capital P of gamma, is equal to, has to be equal to P bar, right? That's the power that we have. So we divide both sides of that equation by P bar, and we get that integration of P of gamma divided by P bar is equal to 1. Okay, that's what we have in on the slide. Now, we found that, remember that we found that P of gamma divided by P bar had this form over here, right? So we just plug this in here, and we find, again, truncation to gamma 0, because below gamma 0, there is no power sent. And then we integrate this function. And so that's how we find gamma 0, right? We impose that this integration is equal to 1. The solution to this equation gives us gamma 0, and then we put that in here, and this other integration is going to give us the capacity. Okay, that's the solution. That's the capacity and the optimum power allocation with CSI. Now, in general, this condition has to be solved numerically. But the nice thing is that it depends only on little p of gamma, which is the fading distribution. So if the fading is Rayleigh, for example, you know what to put here exactly, and if it's Ricean also and stuff. Okay? And in contrast with the case of only receiver CSI, where we showed using the Jensen's inequality, remember, that the capacity was lower than for this equivalent channel with no fading. In this case, that may not be true. So in this case, one can no longer say that fading is always detrimental. If you have CSI at the transmitter, fading may actually be beneficial at the end. So not always, it doesn't have to be, but it may be. So let's look at a very useful graphical interpretation of this solution we just found. Okay? And it's called water thinning. So the idea is the following. You take your channel and you turn it upside down and you form a container. So imagine that this is your channel. So this is gamma over time. Okay, so this is your fading channel. So what you do is you turn it upside down like this. This is exactly the same channel, just flipped over. And then you draw a line at 1 over gamma 0. And you put water until the water top reaches this line of gamma 0. Okay, so imagine you're just putting water. So this brown stuff is water. Up to the point that you get to this, at the top of the water, get to this line. Okay? So the depth of water at each point in time tells you how much power you're going to send at the moment. So in the deep parts, you send a lot of power, like here and here, right? And here, for example, you send no power at all, right? So correspondingly, when the channel is very good, hold on. Right. So here you send a lot of power. Here also. So when the channel is very good, you send a lot of power. When it's very bad, you shut it off. Okay. So let's go back to the formula. So that's what this says, right? So you take a container that moves like 1 over gamma, and you put water until 1 over gamma 0. And the difference, 1 over gamma 0 minus 1 over gamma, so the difference between the top of the water, which is this, and the bottom of the container, which is this, gives you the power. Okay, that's the construction. And this is something that was also found by Shannon, even though the name water filling was found by somebody else, but he found the formula. And then somebody else gave me this name, and this name had stuck. So it's one of the most popular terms in communication, is water filling. Okay? And it's a very useful way of visualizing the optimum way of adapting power. And when the channel is very bad, you have these islands where no power is transmitted. All right? So let's do a quick example. And once again, we'll go back to our three-state channel. Okay, so it's the usual channel. We already seen before the gammas and the probabilities. So let us find the ergodic capacity with transmit and receive CSI. Okay, so first we need to find gamma 0, and then we use gamma 0 to find the capacity. So how do we find gamma 0? Okay, this was the formula, right? Right here. Now, this integration, because we have a discrete channel now, becomes the summation. Right, so that integration becomes this summation. So the summation for all the gamma is bigger than gamma 0 of 1 over gamma 0 minus 1 over gamma times the probability is equal to 1. So we have to solve this equation for this channel. So let's do that. So we want 1 over gamma 0 minus 1 over 0.83, which was the first of the gammas in our channel, right? Times 0.1, 10%, plus 1 over gamma 0 minus 1 over 83.3 times 0.5 plus 1 over gamma 0 minus 1 over 333.3 times 0.4 equal to 1. Okay, that's for the usual channel we've been seeing throughout the lecture. Now, we solve this equation and we clear gamma 0, and we find 0.89. Now, there's a small problem here, right? Because the summation has to include only gammas that are bigger than gamma 0, right? So if we find 0.89, we go back to our channel, we say, oops, one of the values is 0.83, which is below 0.89, right? So this one should not be counted. So, question? I'm sorry?
Didn't you use that the south of gamma 0? So
Yeah, right. So what happens is that the equation tells you that you have to only add those above gamma 0. So you don't know how many you have to add. So the way you usually do it is you start by adding all of them, as I just did. Then you find a contradiction, right? You find, oh, I should not have added the first one. So my assumption that I had to add all of them was wrong. So then I say, okay, so I'm going to take the worst of them and drop it for the summation. So I'm just going to, in this case, I'm going to add just now the next two. And you do that until you get to the point there is no contradiction. That's how you solve it, right? And in this case, you have to go 2 steps. So the first step we go when we find 0.89, we say, oops, 0.83 had to be taken out. So now we take it out, and we do the same thing. Right. Except now take this guy out. We just solve that optimization, that equation, and we find again 0.89. But now we're good, right? Because this time we have no contradiction. So this time both of these are above 0.89, so nothing is inconsistent. So we're done. So gamma 0 is 0.89, and indeed gamma 1 should not have been included. So now that we have gamma 0, we can find the capacity by just applying the formula. Again, let me show you the formula was this one for the continuous channel, right? And for our discrete channel, this integration becomes again a summation. So we have to compute this summation. And again, we only have to add the second and the third gamma. Since we know the first, we know that in this state, when the channel is this bad, we know that we're going to send no power. So this state is off. That's what gamma 0 told us, that anything below 0.89, we shut it off. So for this state, the channel is shut off. And so we only have to compute these two. So we add those two times the probabilities, and we find the capacity is 200.8 kilobits per second. Okay? Now, if you may remember, without power adaptation, the capacity was about 199. So in this case, the advantage of adapting power is actually very small. It is often like that. Not always, but often it's like that. Okay? Okay, so that's the optimum power adaptation policy, the water filling. Now we'll look quickly at 2 suboptimal techniques, okay, which are very interesting in practice. So the first one is based on inverting the fading. So here we're going to say, okay, we'll do something that is not optimum, but it's very easy. So we'll just try to equalize the fading. So let me go back to one of the pictures. Okay, so this is our channel, for example, right? And we know it because we're tracking it. So we'll exactly adjust the power to compensate for the fading so that the receiver sees a flat signal. So when the channel goes up, won't go down. When the channel goes down, won't go up. And we'll just exactly compensate for the channel so that the receiver is going to see a flat signal all the time. That's what we're going to do with channel inversion, right? just what the name says. So mathematically, we'll say that P of gamma times gamma divided by P bar, which is a receiver SNR, is equal to some constant sigma. So this is our target receiver SNR, and so P of gamma can be found easily from this equation, right? So P of gamma is going to be sigma times P bar divided by gamma. Okay, that's what we need to do to equalize the channel. And we know that the average power has to be equal to P bar. Okay, so that means that the average of this has to be equal to P bar. So what's the best gamma? So what's the sigma that we can support? Okay, so sigma is equal to gamma P of gamma divided by P bar. Okay. And we say, okay, since the average of P of gamma has to be equal to P bar, we find that sigma is equal to 1 over, okay, it's 1 over the expected value of 1 over gamma. Okay, can you guys see that, or should I go over it? So we can expect both sides of the equation, right? And find that, okay, so let's see. So sigma is equal to gamma P of gamma divided by P bar. Now we want that the expected value of P of gamma is equal to P bar. Okay. So we expect both sides. We take an expectation on the left and on the right here. We find that expected value of P of gamma, which is P bar, by constraint, is equal to sigma P bar expected value of 1 over gamma. Okay, I'm just expecting both sides. I'm saying the expected value of this, which is the expected value of this, has to be equal to P bar. Okay, so now P bar cancels, and I'm finding that sigma times expected value of 1 over gamma is equal to 1. Okay, so sigma is 1 over the expected value of 1 over gamma. Okay, this is what we have on the board. So the best sigma we can hope for is the expected value is 1 over the expected value of 1 over gamma. Okay, and this is called okay, so then now we can define a capacity, and I'm putting quotes here because this is a suboptimal technique, but it's called the zero outage capacity, which is the capacity of an unfaded channel with this SNR, right? So since we compensate for the fading, now there is no fading at the receiver because we're exactly canceling it out with our control of the power. The receiver is seeing a channel with no fading. So we can just apply the usual formula of log of 1 plus SNR, and so this zero outage capacity with channel inversion is B times the log of 1 plus 1 over the expected value of 1 over gamma. Okay? This is a practically appealing technique because it does not require any rate adaptation, since the channel, as seen by the receiver, is always constant and flat. And so the coding and decoding is fairly simple compared to the other cases. But there is a high penalty to be paid. So for example, with rarely fading, the expected value of 1 over gamma is infinite, in fact. So 1 divided by this goes to 0. And so this capacity is 0. So in other words, with rarely fading, it is not possible to invert the channel. It's just too bad. So some of the the fades are so deep that they cannot be inverted, right? So in other words, when the channel goes to 0 here, sometimes every once in a while, or close to 0, you require an infinite amount of power to invert that. So any channel that has fades that are too bad, too deep, is not invertible. So in those cases, the zero outage capacity is equal to 0. But some of the channels can be inverted. For example, our channel, our baby channel, can be inverted. This guy can be inverted, right? And if you do it, well, you can easily compute that the expected value of 1 over gamma is 0.12, right? So we take these 3 gammas, compute 1 over gamma for each of them, and then multiply them by the probabilities and add that up. And that way you compute the expected value of 1 over gamma. And it comes to 0.12, 0.27, 0.127, okay? So you plug that into this formula. So you compute b times log of 1 plus 1 over 0.12. And you find that this zero outage capacity is 94.4 kilobits per second, okay? And remember that with water filling, we found 200 kilobits per second. So we're less than half with this technique. But it is a very simple technique. So that's the appeal. But it's highly suboptimal. Now, the reason it's so suboptimal, as we saw, is because when the channel gets very bad, it takes a lot of power to invert it. And you just burn a lot of power in those times. So a variation which is very, very, yes?
I had a question.
Oh, go ahead.
My expectation is 1 over lambda is equal to infinity. Because I understand that with gravitating, we can translate it like
Yeah.
0. But the expectation.
So the question is why the expectation of 1 over gamma for the randomly fading channel is infinite. So the expected value of gamma is of course finite, but of 1 over gamma is not. So you can compute the integration. So you have to do this, right? You compute the integral from 0 to infinity of 1 over gamma times p of gamma d gamma. And this p of gamma is the PDF of the randomly fading that is in the textbook. So if you compute this integration, it diverges. So it's just that the channel is, when the channel is bad, it's so bad that the integration diverges. So it is not finite. So that says that the randomly fading channel is a very bad channel. I mean, that is a fact. Okay, so I was saying the main problem is inverting these very bad fading states. So a variation which is much better is the so-called truncated channel inversion, where you suspend transmission in the really bad state. So you say, okay, I'm going to invert the channel, right? Except if it's too bad. If it's really bad, below some cutoff gamma 0, I'm going to give up and say, okay, I'm sending no power. Other than that, I'm going to do the inversion. So I'm going to equalize the power so that the receiver SNR is sigma. So I'm just going to send exactly to the usual inversion. So this approach now all of a sudden has outages, right? Because when the channel is below gamma 0, we send no power, and so the data is lost. And so there is an outage. So in fact, gamma 0 should be chosen on the basis of the outage probability. So so the more outages we can allow, the higher the gamma 0. So how do we compute the gamma that we can support? Well, when we're not in outage, right? So when we're up here, okay, so remember when there was no truncation, we just had inversion. We had that sigma was 1 over the expected value of 1 over gamma. Okay, now it's about the same result. So it's 1 over, and except that we have a modified expectation. That's what this symbol indicates. It's a modified expectation when the integration goes from gamma 0 to infinity. So the integration, which usually in the expectation goes from 0 to infinity, is truncated at gamma 0 in recognition of the fact that below gamma 0 we don't operate. So it's the same equation that you would use to compute the expectation of 1 over gamma, except that you just integrate for gamma 0 to infinity. So between 0 and gamma 0, you turn it off. Okay, that's how you compute sigma. And so the capacity now is b times log of 1 plus 1 over this modified expectation, truncated expectation, let's call it, times 1 minus p out, because now we have outages. So when we're in outage, the data is lost. So we have now this additional factor of 1 minus p out. Okay? And one can optimize this equation to find the best possible outage, right? So you try to maximize these over all possible gamma zeros and see which is the best. All right? So we could consider, for example, the usual baby channel we've seen so far, and play with possible gamma zeros, right? So let's put the channel up. Okay, so let's imagine that the cutoff, gamma 0, is 0.84. Okay? So that means that if the channel is in these two states, 2 and 3, we're going to equalize, we're going to invert it. Okay? If it's in this state, we're going to declare it in outage. Just give up on it. It's too bad. Okay? So we'll have 10% outage, because that happens with probability 10%. And in the other two states, we'll invert the channel. That's for this gamma 0. If we choose this value, 0.84. Okay? If we choose a gamma 0 of 83. By the way, so I haven't finished here. In that case, we can compute the capacity with truncated inversion by applying this formula over here, and it comes out to 192.5. Okay, so if we choose this cutoff, we have 10% of outages and a capacity of 192.5. Now let's take another possible gamma 0, 83.4. Right? So I'm choosing gamma 0 just above each of the gammas, right? Now I'm going here. In this case, we'll have outages in states 2 and 3, right? Because 83.4 is just higher than this. So we have 60% outage, okay? And the capacity comes out to, what is it? 116.4, okay? Which is worse. So between the two values, we want to take the first one, and so we're better off choosing gamma 0 equal to 0.84, which gives us 10% outage and a capacity of 192.5, which is pretty good. Remember that the best possible capacity we found here with optimum adaptation of power was 200. So here we have 192, which is very close. And we have a strategy that is very simple, this inversion and truncation. Okay, so the best way to compare these capacities is by using a plot. So in the textbook you have comparisons for log normal, Rayleigh, and Nakagami fading. And let me put it up. Okay, so here's one. Okay, Rayleigh fading, this is good. Okay, so here we have on the horizontal axis we have average SNR, so this would be gamma var, and here we have C over B, so this is C divided by B, so it's log of 1 plus whatever, right? So we have the stars indicate the capacity of a channel with no fading. So this is this usual equivalent channel that has the same average power but no fading, which is an upper bound, as we saw, right? So these are the stars. Then the solid line is the capacity with transmit and receive CSI. So here we're doing the water filling, this temporal water filling that we derived. That's the solid line, which is the second best. And the dashed line is the capacity with only receiver. So here we don't adapt the power. And we lose very little, as we saw before. especially up here, it's almost indistinguishable. Then this maximum outage capacity is the truncated channel inversion that we just saw, which is also very competitive. And it's a very simple strategy, and it's pretty good here. So this is inversion with truncation. And finally, the full inversion with no truncation, which is the zero outage, is down here because it's zero in this case, right? So this one is really bad, and these ones are all not that far from each other, as you can see. You have also plots for, as I said, Nakagami fading and whatnot. Okay, so I think we're going to stop here, and we have about 6 or 7 slides. We'll cover it quickly next week, and then continue. Okay? Have a good week.